Ich habe ja schon
Okay, everyone, just go back to the seats, please. The live stream is not working, so we are now live as well. So if you please have a seat, we will continue with the next talk. On the Meetup page. On the Meetup page to our YouTube channel, and on the YouTube channel you see a video of the last one and of this one now, please.
Ich muss nach meinem Vortrag gleich abdampfen. Ich muss noch nach Buchreis. Oh, krass. Ja, ja.
Wo muss ich drücken? Weil das war einfach Konfusion. Okay.
Warte kurz. So, okay guys, we will now start with our next talk. It's about quantum machine learning, and I just wait for the other ones in the back to be quiet. Okay, if you please come forward and have a seat. Okay, so the next talk will be about quantum machine learning from Matthias, and it's going to be an introduction talk, I think.
Yeah, just an overview.
Okay, so thanks, and thanks, Joe.
Well, thanks, Marcus, for the introduction and for having me today, and thanks for coming. Yeah, I'm going to talk about quantum machine learning, and I mean, it looks a bit like a clash of buzzwords, but I hope I can tell you or show you that it actually might be an interesting thing to think about for the next decade, let's say, in quantum computing. And in particular, I will focus on generative models, because I think that's one of the approaches in machine learning that might be suitable for, especially for near-term quantum computers. And we've had an introduction to quantum computing, and especially on near-term quantum computing by Michael just before in the previous talk. So I'm not going to repeat all of that. You know all of that about that now. I'm also not going to talk too much about actual implementation of quantum computers because we have another talk coming up talking about actual implementations. So, oh, that's the wrong direction. Yeah, same problem. It's somehow flipped around, I think. Who am I? Name is Matthias Rosenkranz. Briefly, I did my PhD in theoretical physics. Basically, I was working in quantum simulations using ultra-cold atoms. So that's basically the idea of what some people call an analog quantum computer, where you simulate a quantum system using neutral atoms, which you can control in a very ideal way. And you can basically use it to simulate other systems, other quantum systems. Then I did a postdoc and joined DeFi in 2013. And I'm mainly serving clients in the finance sector at the moment. And my specialization is in market risk and machine learning. So that's what my day-to-day work is, basically. But I'm also steering a quantum technology initiative at DeFi, which we initiated last year. And well, this is part of the reason why I'm going to introduce you to this topic today. So, no, doesn't want to. No, that's the wrong one. Okay, I want to start this with a quote from a recent article by Hennessy and Patterson. So these are two guys who won the Turing Award a couple of years ago. So one of the big computer science prizes. And they said that the n-of-Dennett scaling and Moore's law are not problems that must be solved, but facts that recognize offer breathtaking opportunities. And they call this article, or they ushered in a new golden age for computer architectures. And that is somehow the framework that I see quantum computing in this whole machine learning topic. It's a kind of specialized architecture, specialized computing architecture, which can solve certain subtasks in machine learning problems. So, no, doesn't want to go the right way. How does it look like, the landscape in machine learning training or machine learning hardware approaches? So what we've seen over the last few years in machine learning is basically people started using normal CPUs to train their machine learning methods. They ran into problems when they wanted to basically train deeper and deeper models, so what you call deep learning nowadays. That became hard to run on CPUs because you have to multiply big matrices, etc., etc. So people started using GPUs, which are more specialized computing architectures. They are specialized in the way that they can parallelize certain tasks. So they are very good at executing parallel computation. But that still wasn't enough for some tasks. So people started using FPGAs and ASICs, etc. So these are extremely specialized computing devices. So that's part of this idea of Hennessy and Patterson, that we live in this age of very specialized architectures. So these ASICs, it's a picture of a Google TPU. It basically does nothing. So all the soldering, all the wires here, they do nothing but multiply matrices. So that's a processor that just multiplies matrices. And this is something that you need if you want to train basically deep neural networks. So this is a device extremely specialized for these kind of highly parallelizable tasks. And in a similar way, you can view basically quantum computing in an abstract way. You have, on the one side, you have a universal quantum processor. This is the, say, equivalent to the CPU. You can run universal computation in principle on it, but we are far from having that. Where we are at the moment is in this so-called NISQ area. It's a term that was coined by Preskill a couple of years ago. John Preskill, a well-known physicist, he called it the noisy intermediate scale quantum era. So this is an area where we have noisy qubits. We have small to medium scale sizes and not quite or fairly low connectivity between the individual qubits. So qubits are the quantum equivalents of bits on a classical computer. And basically what we have nowadays is basically these kind of simulators, what some people call it a simulator, small-scale quantum computers that can run small algorithms. And what we also have is quantum annealers, and I mean they are a bit on the right, so they are a bit more specialized than these quantum simulators in some sense, because they are made basically to solve a certain kind of optimization problems. Whereas quantum simulators in principle can run also more general problems, or more general algorithms than just optimizing certain problems. Yeah, so this is a kind of trend that, that we've seen in machine learning basically. And I mean the idea, if I go back, would be that if you have a highly parallelizable task like multiply matrices in a deep learning task, then you're probably better off just using a GPU at the moment. But if you have other problems where you maybe have a model that can't be parallelized in this fashion, where you have some kind of highly correlated problem that has somehow a global structure, like if you think about Ising models, etc., then you might be better off thinking about how you could perhaps implement this on a quantum computer. So this is the idea where, well, this is one idea where quantum computing could help in machine learning, where you have these kind of more complex problems. This is not something that is just some abstract thinking in academia. Quite a number of startups have come up over the last few years. I've tried to scrape them off the quantum computing report here, and I did some own research and tried to plot where they are based approximately. So most of this, the startup scene is located in North America. But there are also a number of them in Europe actually. I don't know, HQS, if you do quantum machine learning, maybe. So, yeah, okay, because I don't have anything in Germany here, so that's why I was asking. Okay, and there's some highly prominent people involved in Zapata computing. It's a spin-off from Alan Asborougousik's group, which, I mean, they basically, or he came up with this algorithm that HPS uses, for example. Xanadu is fairly well known in this field. So that's some kind of startup scene coming up, investing in these kind of ideas. So let's have a look how it actually fits into the picture. So here's a very abstract way to think about quantum computing. So we had an introduction. You know about qubits. The way I think about quantum computing, for the sake of this talk, is a quantum computer is a machine for basically preparing and sampling from probability distributions in an abstract way. So you can think of, in a classical sense, if you think about how would you generate a normal random variable on a classical computer. What you do is you take an easily prepared random variable, random number, uniformly distributed, and you send it through an algorithm. It's called a Box-Muller algorithm, for example, and it basically transforms you this, or actually two uniformly distributed variables into a normal variable. And this is, in an abstract way, quite similar to what a quantum computer does. You start with a fairly simple distribution at the beginning. So if you initialize your algorithm, if you would look into your quantum computer, if you open the lid and measure the system, you would find the typical algorithm, it's a uniform distribution, so everything is, every possible state has the same probability of appearing. But you close the lid, so you don't actually look, and instead you send it through a quantum algorithm, which basically transforms this probability distribution through a number of gates. So these are the gates that you saw on the previous slides, on the previous talk. and at the end you measure this state. So these boxes here are basically measurements, and this transforms it into a classical sample of a bit string, basically. And what you get in the end is some kind of distribution of possible outcomes. So this state here has a high probability. So a way to think about quantum computing is, or a quantum algorithm is that it takes a simple distribution, transforms it in such a way that your solution has a high probability of appearing at the end in the measurement. And this way of thinking is, I think, is quite helpful for applying quantum computing in machine learning as well, which is, yeah. So I will quickly recap machine learning because I'm not sure if everyone is familiar with the terms, and I will also introduce you to yeah, the more probabilistic way to think about machine learning. So, in a broad sense, there are about 3 categories of machine learning that people typically categorize. So you have supervised learning and unsupervised learning, and you have reinforcement learning. I am not going to talk about reinforcement learning here because I mean it's useful also for quantum computing, especially for quantum error correction, for quantum control, but I'm just not going to talk about it here. So instead, we're going to focus on supervised and unsupervised learning. So in supervised learning, the problem is that you have data, you have labels, so you know the labels of these data, and you try to train your computer to predict basically the label if you give it a new data sample. So a typical question you ask is, what's the label of this data point? So this picture here is an example. So you have some data points here, and you have some blue dots and some orange dots here, and they could represent, say, some kind of disease. So these are, I don't know, the axes are, I don't know, height and weight perhaps of a person, or some kind of drug interaction. And blue dot means person has a disease, orange means person doesn't have a disease, and you want to find some kind of a plane or generalization of a plane that separates these two kinds of dots. So if you then have a new dot, a new data point coming in, you can tell, okay, it's lying on the right side of this line. That means this person doesn't have the disease. So that's the idea in supervised learning. You have some kind of historical data with these labels, disease or not disease, and you train your algorithm basically on this data. There are a couple or a number, or quite a lot of approaches for these kind of problems. Broadly, you can distinguish between generative models and discriminative models. In generative models, the idea is that you learn basically a joint probability distribution of your data. So you learn a distribution of your labels and your data, joint distribution, and then apply Bayes' theorem, which gives you probability of a certain class. So either being here or here, having this label or this label, given a data point. And in discriminative learning, you don't have this probabilistic thinking. And here you have methods like support vector machines. It's a classical or traditional machine learning methods which does exactly this task here. It separates data points in a high-dimensional space. On the other hand, you have unsupervised learning, and the difference here is that you don't have labels on your data. So your algorithm only sees a bunch of data coming in, and it somehow has to figure out how this data is structured. So in this example here, you feed in a bunch of cats and dog pictures, for example. They all look slightly different colors, different angles, etc. But algorithm figures out that, okay, these pictures look somehow similar, and these pictures look somehow similar, so it figures out that there are probably 2 clusters in this data set. So a typical question you would ask in a supervised learning cell is, what is the structure of my data? Or in a more general sense, how was the data generated? So how are these pictures generated? So the basic idea here is often, especially in these generative models, is that you want to find, again, a probability distribution. If you think about pictures, you want to find the distributions of pixels, basically. And of course, you can imagine a picture has, say, 1024 by 1024 pixels. It's 1 million data points. You have millions of pictures. It's a quite hard task. So this is actually often harder than the supervised learning problems that you see. And there are a bunch of quite successful methods, especially over the last 5 years, especially these generative adversarial networks. You might have heard about them. I mean, they generate extremely realistic looking pictures. So basically, you can't distinguish them from real pictures anymore. They generate pictures of faces, for example, that you can't basically distinguish anymore from real pictures. But they are completely randomly generated. And there are some other kind of probabilistic methods to approach these kind of problems. Okay, here's a bit of structuring the whole quantum machine learning field. And what I want to focus on is basically this upper right quadrant here. And I mean, this labeling here just means that C means classical, Q means quantum. So here, I mean, this is a classical algorithm, and you feed in classical data. So this is classical machine learning on this quadrant. Here you have a quantum algorithm, but you feed in classical data, and you can do other combinations as well. So we're going to focus on this side in this talk. So over the last, say, I don't know, perhaps 5 years, at the beginning people started to think about this box. So there was one paper, it was called an HHL, it's an HHL algorithm, named after the authors of the paper. I mean, it's in the references down there. This is basically an approach where you quantize your matrix inversion. So as we said, I mean, in deep learning, often you multiply matrices or you have to invert matrices. It's basically linear algebra problems, high dimensional. And this was an algorithm that solved that problem exponentially faster, given some assumptions. So this was used as a base for many of these classical machine learning algorithms to transport basically these classical methods into a quantum domain. So you have, for example, quantum support vector machines, you have quantum linear regression, etc., etc. And we're going to talk a little bit about this on the next slide. Basically, you need a universal quantum computer for these problems, for realistic sizes. Another approach is these probabilistic methods that I briefly mentioned before. And this is something that came up over the last few years when people started thinking about how to use these NISQ era quantum computers that we have in the near term. And in these methods, often you need samples from the probability distributions, and this is somehow the connection to this thinking about the way of thinking about quantum computers in probabilistic terms. But this kind of thinking helps. So as we will see, basically in these methods, it's very natural to replace certain steps by quantum computer. Okay, the lower ones, I mentioned them here, but I'm not going to talk about it much. There are other interesting ideas, of course, but this is our focus here. Okay, what's the problem with these, or potential problem with these upper algorithms for the universal quantum computer? So this HH algorithm, in principle, as I said, exponential speedup, that's nice. But in 2015, Scott Aronson wrote often quoted paper where he pointed out four caveats of this algorithm. And this is a slightly different way of saying or of phrasing these 4 caveats here. Basically, you have an input problem with these methods. So you have certain assumptions about your inputs. You have certain assumptions about outputs that are a problem on near-term quantum computers. You have size problems and a benchmarking problem. So the input problem means that in this HHI algorithm that you need for many of these traditional quantized methods, you need to encode your classical data basically into the amplitude of your qubits. And this is very hard to do, exactly. And so basically you need a device which is called a quantum random access memory, QRAM, which doesn't exist yet. So people are skeptical if you can really scale this, or how to get around this input problem in the near term without access to this QRAM device, which would basically allow you to read classical data much faster. And if you don't have this, then basically reading classical data becomes the bottleneck of the whole algorithm, and it breaks down your whole speedup. You have an output problem. You have to read out data. You have to you basically encode your solutions again in the amplitudes of qubits, and you have to read it out. And doing that with sufficient accuracy, again, can destroy the whole speedup that you see in the actual HHI algorithm. You have a size problem. How do you actually implement the gates, the number of gates that you need to invert these the matrices? So basically, how do you actually implement the algorithm on a small scale or relatively small scale quantum computer with maybe 50 gates or say 100 or a few hundred gates that we will have over the next 5 to 10 years. And you have a benchmarking problem, which is true for all methods, I guess. How do you actually compare in a realistic way if your method is faster than a classical algorithm? You have to run a lot of benchmarking to actually prove that it's faster. So people have started doubting this a bit, this kind of approach, and actually there was a series of papers last year by Yuan Tang, 18-year-old student, mentored by Scott Aronson, I think. So first, and it was last year, it was a bit of a tough year for quantum machine learning. So first she wrote this paper on, where she basically said if you assume that a classical computer has the same kind of, if you can make the same assumptions for example, your input problem that you make for this HHI algorithm, then these kind of algorithms don't actually have a speed up anymore quantumly. So you can actually implement them on a classical computer and it runs basically at the same, asymptotically in the same speed. So she took down the quantum recommendation system paper, and then there was a paper which showed basically similar thing for the quantum PCA. The PCA is a principal component analysis, which again was an algorithm that could speed up principal component analysis. And finally, she even attacked HHL itself for low-rank problems. So HHL is still for non-low-rank problems, it's still valid. But for low-rank problems, you can actually show that you can solve it asymptotically with the same speed as on a classical computer, basically. I've stolen this picture from Twitter. If you're interested, if you're into that kind of thing, check out quantum meaning. And what I want to say, I mean, quantum machine learning has also inspired classical machine learning methods. She showed basically that you can get exponential speedup on a classical computer if you assume you can do certain operations classically in the same way that you can do it, assume it on a quantum computer. Okay, so what's left? So we have, what kind of potential advantages do we have using quantum computers for machine learning? We have speed. So these are the typical kind of speedups that you see, super polynomial or exponential, slightly less. HHL is an example, it's almost exponential speedup for certain linear algebra problems, polynomial speedups, and you have some heuristic methods. On the other hand, and what I think is potentially more interesting in the near term, it's not only speed, so speeding up the training, but you can also have more complex problems, basically, or more complex models. So if you think about probabilistic machine learning methods, often you assume some kind of simple distribution, because it's simple, basically, and you can sample from it classically. And now if you have a quantum computer and you can sample from more complex distributions, this could be a potential way to address more complex or to model more complex relationships in these machine learning methods. Yeah, so people looked at Boltzmann machine, which is a classical machine learning model, basically. You can implement that on approximately on a quantum annealer. So that was the first approach, basically quantizing this Boltzmann model, which basically is it requires you to sample from a Boltzmann distribution, which is classically hard to do, but you can do it approximately on a quantum annealer efficiently. And then people also showed that one can translate it to a gate model approach. So this is more like the qubit picture that we saw earlier, these lines and transformations on qubits. And there are other ideas. Okay, so what I want to focus is generative models. So in general, richer models in the NISQ area, richer models for machine learning using quantum computers. And how do we do it? Basically using variational frameworks. And I mean, this is similar to what Michael said just before. It's a variational approach which has become extremely popular over the last few years for approaching near-term quantum computing algorithms. So these are the two basically pillars that I will go through over the next couple of slides. So generative models, I'll just spend another slide on what is actually a generative model. And here just some examples of what they are used for. So it's a probabilistic model of data. And basically people use it for chemistry, for materials and medicine. So basically the idea is that you can, you have a model of a material and you can basically simulate how materials change, how drugs or chemistry problems change by changing basically the inputs of your model. You can generate images. This is the example of generating faces or generating images in general. And another thing is speech synthesis. So if you have an Android phone, your Google Assistant basically uses a generative model to synthesize speech. It's called a WaveNet, which is basically a generative model. Takes in text and outputs speech that is fairly realistic. Okay, cartoon of how a generative model works. So you pose a probabilistic model. So this is called a graphical model of a probability distribution. So these dots here, they are basically stochastic variables. And arrows, in this case, they indicate how these arrows basically relate to each other. So this variable would depend on this one, this one, this one, but this one doesn't depend on this one. So it's basically a way to structure your probability distribution. So this picture would tell you that, okay, my points down here, they all depend on one variable up here. So if you can write this model as a joint distribution of all these variables, and this gives you the conditional independence of this model. What you feed in at the bottom, these orange points, it's basically the data. For example, it could be images of faces. So these would be, for example, pixels. And at the top, you feed in random variable. For example, a Gaussian, just a randomly drawn random variable. And what you then do in your training, you basically loop through all your data points, all your pictures, and you try to optimize this probabilistic model in such a way that at the end you have a trained model, so all your parameters are fixed now. And now if you plug in a number here at the top, it will generate you a realistic picture, for example, at the bottom. So this would be this way. You can also do it conditionally, so you can tell it, okay, if I feed in, let's say, negative numbers, it outputs me smiley faces. If I feed in positive numbers, it will output me frowning faces. So that's something you could control here as well. Another way is you can turn it around and you can say, okay, I give you a picture, what does it show? So you feed in data, you feed in a picture, and it will tell you, okay, this is a picture of a smiley face. So this would be an inference step the other way around, basically. So this is a very rough idea of what a generative model does. A bit more technical now, on a more technical level. Let's start on the classical side. So this is again the graphical model of your probability distribution. It's typically separated into a data kind of space. So this is a visible layer. This is where your data comes in. And this is a latent space. So these are variables that you don't observe. So this would be, for example, the picture. And this would be a variable that says frowny face, smiley face, for example. And in between, so this is this graphical model tells you that this variable here depends on this one. So the probability distribution is a conditional one. And basically, if you want to go from here to here, you can feed this through a deterministic function. So to get the parameters of this distribution down here, you take a variable here, feed it through a function, and get your parameters for your distribution here. And this function here is typically, in machine learning, you use neural networks as your deterministic function here. And you fit parameters of this neural net in training. There are several approaches to train these kind of models and improve them. Sampling methods, they use Markov chain Monte Carlo methods. There are more optimization approaches. This is then called a variational inference problem. Or they are likelihood tree methods. This is the kind of generative adversarial networks that I mentioned before. Okay, so where does quantum fit in now, quantum computer? So one way would be you just replace this whole thing by a quantum computer. Because we said a quantum computer in an abstract way is just a device for preparing probability distributions. So you have a probability distribution here, just replace it by a quantum computer. And then you optimize basically your parameter inside your state on your quantum computer. You sample from this, and the samples gives you a sample from this distribution. So this would be kind of a full quantum approach. But you can also do it a bit differently and say, okay, the layer down here, the data space, it's a high-dimensional space. Picture, for example, has millions of variables. You're not likely to fit this into a quantum computer. But this latent space is quite often low-dimensional. So if you have as a dimension only frowny faces and smiley faces, for example, it's a two-dimensional space. So this is something that is more realistic to fit on a quantum computer. This variable up here. So this is another idea. You basically plug in your quantum computer in your latent space, sample from it, and then you can also still feed it through neural net if you want, or you can just directly plug it into your classical distribution down here. And this is a potential way to approach quantum machine learning in the near term. Low-dimensional space for a quantum computer, high-dimensional space for a classical computer. How do you actually train it? And here this is the kind of variational framework, the variational idea that has become so popular over the last years. It's basically the idea that you let your quantum computer do what quantum computers do best, sampling, and you let your classical computer do what it does best. This is, for example, in this case, optimizing certain objective functions in some higher dimensional space. So what you do in an abstract way, and here's a bit more concrete, but you prepare your quantum system in a state which is basically characterized by the gates that you apply. At the top, these boxes, there are two examples of two approaches how you could structure your circuit. These are the two basic approaches that people look into. So here again, you have this kind of circuit model. You have some gates, arbitrary gates, whatever. It could be rotations or something. They have some parameters, alpha 1 to alpha 3 in this case. So it's 3 qubits here. And then you have these 3, say, rotations, for example, with 3 angles. And then you can apply these interactions between them. Then you have another layer with different parameters. This is one approach. And another approach is if you have some kind of structure in your problem. So if you want to solve if you think about Boltzmann machines are basically derived from a certain Ising model, which is already a probabilistic model. So you have a certain correlation structure given already in your model. That basically you can map directly on your quantum system. So if you have a probabilistic model that looks like this, so node 1 is correlated with node 2 and 1 with 3, but 2 and 3 are not correlated, you can directly model that in this way. For example, you say, I correlate only 1 and 3 and 2 and 1. And then I have, for example, 2 parameters here. Once you have that, so you have this variation circuit prepared on your core computer. You basically sample from this state, which means you just measure it many times. And then you have a sample, you have bit strings basically. You can plug them into some kind of objective function. So you assume that you have some kind of function, for example, an energy functional that you want to minimize. You plug in this bit string, you get an energy. And then classically, this is down here basically, classically you optimize the parameters now. So you have basically a mapping from this sample to some objective function classically. You optimize this function, which gives you a new set of parameters, and then you plug that into your state again. So you have now A prime, B prime, maybe gamma prime. You plug in these new parameters and repeat the whole thing many times until, for example, you have reached some kind of optimal condition. For example, it could be that you want to train, or say that the frequency that you see your data points, your bit strings in your data, should match the marginal likelihood of your model that you train. So that could be an objective function down here. So that what objective function you use, and that depends on your model, etc. But this is kind of the rough idea of how this variation framework works. And there's a big caveat, recent paper by Google guys. This was the infamous Barron Plateau paper. This approach over here, I mean, it looks generic, it looks nice, because in principle you would think that you can somehow represent everything here with this kind of approach. You correlate everything with everything. You have many parameters to optimize, but they showed that actually if you apply typical training algorithms, so if you these typical algorithms, they use gradients, gradient descent methods, for example, to optimize these parameters. And they showed that basically the gradient of this thing is 0, basically. So you can't actually train this method. So this is a problem if you scale this up, and this will be interesting how this develops, if this is really going to work on practical problems. And this one doesn't have this problem in the same sense, but this is a caveat that we have here. Okay, just quick one on software. There's actually a lot of software out there already, so you can actually go out and program these kind of things. And I've just listed a few of the software packages. I mean, we talked about Rigetti. They have a software package called Forest. Quite interesting software package is PennyLane. No, at least I find it quite interesting. It's similar to, in idea, it's similar to TensorFlow, but now you don't only have a classical computational nodes. So TensorFlow, you have basically nodes. You build up a computational graph. Here you can also have quantum nodes in between, and it does automatic differentiation, etc. for you, similar to TensorFlow, across quantum and classical nodes. So very interesting. And software, you can actually go out and try out these things. And this is actually something that I want to advertise here. I mean, these kind of approaches, it's out there. We don't quite know if it's really useful, so it's actually important to try it out and come up with use cases and explore these things. So my message would be probably focus on probabilistic models, because that seems to be a sensible approach for near-term quantum computers. Focus on hard distributions that you can't sample classically, perhaps, because there you might actually see some advantage on a quantum computer. focus on variational frameworks, and software frameworks exist, so you can go out and actually try it out on simulators. And here are some contact details if you're interested in this. Okay, thanks.
Any question?
Yeah, I mean, I really like it that you cite this Baron Plateau paper. I mean, it's really important. In fact, I just want to comment that we are actually a little bit afraid that even for structured approaches, like coupled cluster, it even seems to be still a problem. I mean, the proof is not valid, but still it seems could be a problem still even for structured approaches.
I mean, for small qubit counts, you don't see it yet, but that might become a problem if you go beyond 20 qubits or something, perhaps.
Yes. So that's just a question. I mean, did you ever look at this? There is a work by some guy from IBM, Smolin, on training on noisy data. Are you familiar with that work? No? Yeah. Yeah, this Smolin. No? Okay, maybe we talk later.
I'm not sure who you
Any other questions?
Yeah.
So, thank you. It was very insightful. My question is, when you talk about probabilistic models, do you think there is a potential of misusing those in, I don't know, hacking into your passwords or encryption decoding, and also when we talk about some application regarding synthesizing voice, for example, and face recognition, do you think you have potential in this area?
I mean, regarding your first question, hacking into, I don't see a direct application yet about hacking into anything here. I mean, are you referring to tracking RSA, these kind of things? Or?
Yes. Yeah.
I mean, these are not algorithms that are used for factoring primes that you would need.
Yeah, not really with these, but I'm just asking as imagining, can this be potentially be misused?
Yeah, I guess I think every method can be misused, but I don't see a direct link for tracking anything here. Not much really.
And what about the face recognition or face picture generation and voice?
Yeah. I mean, we are not there yet on a quantum computer that we can actually produce realistic face images. So what people do at the moment is more like generating data that is basically zeros and ones. So basically, you generate data that is bars and stripes, basically. So we're not at the stage yet where we can generate realistic-looking images with quantum methods. So this is the square in the classical domain. So I think these kind of ethical problems you would have first on a classical machine learning side. And I think there's the whole field of adversarial training and problems of faking IDs by generating fake images. So I think this will come up in the classical machine learning before it would be relevant here.
Yeah.
But it's probably something that one needs to address at some point.
And is there something where we are addressing, so as quantum computing is becoming more popular and important, and I can vital for our growth as human beings, is there a moral standard or somebody is looking into it?
I know there is a group, Quantum Ethics. I know them from Twitter only. I'm not sure who actually runs it. But I know that people have started looking into these issues. And if you look on Twitter, it's Quantum Ethics or something like that. You search for that. There's a group looking into ethical issues. Yes.
Okay, thank you.
Hi, many thanks for this really insightful presentation. A question. I got in a fight recently with a colleague, and I think she's also a theoretical physicist, and she's super skeptical about QML in principle. And I guess now that she probably read a lot of stuff you and Tang wrote, do you think that we are at the end of this, or that many other potential applications of quantum machine learning may be put off the map?
Yeah. You and Tang perhaps put an end on certain types of algorithms. mainly on HHL-based stuff. So a lot of the previous papers that we saw, actually based on stuff based on linear algebra problems. HHL is still relevant or still applicable to dense matrices. There's a proof, I mean, it's still exponential beta for dense matrices. But I don't see a practical application in the near term. So that's why I try to shift the focus here a little bit. I go away from this kind of more traditional quantization of classical methods and looking to more these variational probabilistic frameworks, because there you don't need exact readouts, etc. It's not a problem if it's noisy, because you sample many times anyway, you look at averages, etc. So in this framework, I still see potential. The traditional ones, I would skeptical.
Do you think that Ewan might tackle this next? Is she done, or could there be?
I mean, as I said, dense HHL, she won't track.
Okay.
But I guess basically everything that is somehow based on HHL is potentially is potential for takedown.
Okay.
I think she's doing a PhD now.
So how many? I think it depends then on how many papers she needs to publish to get her degree, right? So maybe once she, maybe she will do a postdoc and take down even more stuff.
There was another meme that I put in here is that at the previous QRP conference there was a fake schedule which had only you and Tang. Each slot. So,
Thanks.
Any other questions? So thank you, Matthias, again. So now we're going to a more hardware talk from Ulrich Poschinger from the University of Mainz, and he talks a bit about iron traps. So thank you.
Yeah, thanks a lot, Markus, and thanks a lot for having me. It's a big pleasure to be here and actually talk about how to build a quantum computer, right? And I'm going to present activities which are going on right across the Rhine in Mainz. That's flipped, right? Okay. Okay. So that's an overview on hardware platforms which are possibly allowing for implementations of quantum computers, which I stole from some reference. This overview is not necessarily complete and also not entirely correct, but anyhow, I've been highlighting two platforms, superconducting qubits and trapped ions, which are currently spearheading the field. With spearheading, I mean that these platforms up to date have shown implementations of multi-qubit systems at decent gate fidelities and also realizations of small-scale quantum algorithms. So the main difference between these two platforms is that the superconducting qubits are devices, they're man-made, while qubits based on trapped ions, so the qubits themselves, are made by nature. So they're all identical. That's the basic difference between these two approaches, and I'll show you the implications of this in the following. So that's the right direction here. So, of course, for trapped ions, you also need machinery around them. In this case, an ion trap. That's what a modern ion trap looks like. I'll come back to that later. Then in this kind of trap, you can trap ions, image them on a CCD camera. Then you get a beautiful image like that. So that's your qubit register. And if you look at each trapped ion itself, it's essentially an atom. So an atom, here we know this Bohr atom picture, perhaps from school, where electrons are orbiting around the nucleus. So in a more quantum mechanical picture, each of these orbits here corresponds to some electronic state or level of the atom, and electrons can be driven between these levels by irradiating them with suitable laser radiation. So that's how we operate the qubits. So in the following, I'll first show you how we trap ions, how we manipulate them in order to work as qubits. Then I'll show you some details and challenges of the machinery we need to implement these things, and finally I'll show you some recent results and future challenges. Trap ions are charged particles. That's the nice thing about them. The charge can act as a handle in order to confine them in space. That's necessary if I work with atoms. Yeah, they need to be somewhere at a fixed location in order to manipulate them. And the device which allows for doing that is the Paul trap, which was awarded with the Nobel Prize in 1999. So that's a very simple schematic of the original Paul trap. It consists essentially of two electrodes, one ring electrode which is grounded and electrodes which have radio frequency voltage applied to them. So that's a rapidly oscillating voltage which gives rise to an electric field, which is given by these red arrows here, which has a so-called quadrupole structure. Yeah? And if an ion sits off the trap center, it experiences a rapidly oscillating electric field. So it undergoes some rapid shaking motion, which is called quiver motion, at an amplitude which is given by this expression here. So that's the charge, the mass, the frequency of the drive, and what's missing here is, of course, the strength of the electric field. The catch here is that this quiver motion stores energy, so it can act as an effective degree of freedom, as an effective potential. And as we know from elementary mechanics, particles like to minimize their potential energy, like in a gravitational field. So in this trap, there's an effective restoring force of the charged particle towards the trap center. So if I combine this with laser cooling, which is indicated by this blue arrow here, we can confine an ion at the center of this trap and cool it even close to the quantum mechanical ground state. So this trap in its original form is not useful for quantum computing, but now we look at the next stage of the evolution of Paul trap, which is the linear Paul trap. It's a bit more complex. So here we have still the RF electrodes, the ground electrodes, and additionally we have DC electrodes, and this linear structure here. So we have this RF confinement in the radial plane and confinement by DC fields along this direction here. Yeah? And if I look at this simple picture here, if the radial confinement by the RF is stronger than the axial confinement given by the DC voltage, then if I have several ions in the trap, they arrange themselves in this kind of string structure here. Yeah? And that's a picture I've been showing you before. So that's a register of trapped ions which can act as qubits. So now let's look at the ions themselves. So that always takes a while. Yeah. So first we have to decide which kind of atomic ions we want to use, and the ions of our choice more or less always come from the second group of the periodic table. It's the alkaline earth ions, and the reason for that is that alkaline earth atoms have two valence electrons. So in this outer atomic shell here, there's two electrons, and with photoionization done by lasers, I can kick one of these electrons away. So what I'm left with is, in a simplified picture, one valence electron on the outer shell trapped by a positively charged atomic core. Yeah? The advantage here that this is a very simple atomic system, so it has a very simple hydrogen-like level structure and allows for easy, straightforward manipulation by laser beams. So now if I look at a level scheme, in this case it's calcium-40, the ion of our choice, and I show here a part of the level scheme. I have a ground state and I have an excited state. In this case it's called D state, and the remarkable feature of this D state is that it has a lifetime of 1 second. So if I put an electron in this state here, it takes about 1 second on average until it decays back to the ground state, and that's by far enough time to do quantum state manipulation. So the qubit is implemented by these two electronic levels here, and then I also have a very short-lived P state, which can also be addressed by lasers. This state, in contrast, decays on a time scale of about 7 nanoseconds. Yeah, so if I keep on shining my laser in, it always is excited and decays back. It's emitting photons which can be detected, and this way I can read out the state of the qubit. So this qubit is called optical qubit because the qubit is comprised by the ground state and the metastable state. That's successfully used by the group of Rainer Blatt in Innsbruck for already quite complex demonstrations of quantum algorithms. In our case, in Mainz, we use a slight variation of this. So we encode the qubit in the spin of the ground state. So we don't use the metastable state here for encoding the qubit, but our qubit is really given by the spin of the valence electron pointing up or down in an external magnetic field. Yeah? So this can be manipulated in a more simple way. The only drawback here is that still transferring population to the metastable state is required for reading out the qubit. The most complex step for any given architecture is driving entangling gates between several qubits. In this case, it's very important to realize that trapped ions are strongly coupled by the Coulomb repulsion. So we realize gates by shining in a bichromatic laser field, so it's 2 laser frequencies, and together with the Coulomb repulsion, these 2 driving laser fields generate an effective spin-spin interaction, which gives rise to entangling unitaries. So a lot of work by several groups worldwide has been done on improving gate fidelities and also increasing the capabilities. So by now we can do multi-ion gates, so we can not only entangle 2 ions, but up to 16 ions, for example. Then also recent technology allows for entangling like 2 out of n ions in a string by laser addressing. And also a very nice recent development is the realization of very fast gates on a time scale of about 1 microsecond. So we can really beat the speed limits given by the confinement. So here's an overview on the evolution of the fidelities of these entangling gates for various platforms. So that's gate error rate versus year. So we can see an ongoing decrease of the gate error rates due to technological improvements. And as you can also see, laser-driven gates are still a bit superior as compared to superconducting qubits. However, this picture doesn't convey the full truth, to be honest, because we always have to distinguish component performance and system performance. So all these demonstrations here have been carried out for isolated building blocks of 2 ions, or superconducting qubits, for example, or small superconducting qubit devices, but the picture really looks entirely different if I have a multi-qubit system. So realizing a gate of, say, 99% fidelity is rather straightforward nowadays with 2 trapped ions isolated in a simple trap. But if I want to go for, say, 100 qubits or so, it's a very much different story. Yeah? So the remaining step I briefly talk about is readout in order to make clear what we do. If we go back to this optical qubit, as I said, for reading out, we shine in this resonant light here, driving the S to P transition. If the qubit has been in the logical S state, I keep on cycling this transition and emitting photons. If the qubit is projected to the D state, it's not addressed by the laser, it's dark, so I don't see any light. Yeah? So if I count photons, for example, on a photomultiplier device for a given time duration, say of 11 microseconds, for the dark state I hardly see any photons. For the bright state I see quite a bit of photons, yeah, and that's the way I discriminate my logical state upon readout. So the next topic I want to address is scalability. As for any viable platform under discussion for quantum computing, that's really the key challenge, scalability to go to systems of, say, 800 qubits, 1,000 qubits, and so on. And it's apparently clear that this approach here, linear ion strings in a classical Paul trap, doesn't work. Why? Trapped particles repel each other, they don't really like each other, so if I keep on increasing the size of the register, I get structural instabilities. Also, it's impossible to read out single ions anymore, or even to address them with laser beams, so that's not the way to go for scalability. But a solution was proposed already quite some while ago by the group of Nobel laureate Dave Wineland. So this would be building a microchip Paul trap, which is consisting of many electrodes. Yeah? So it's a segmented Paul trap. And here's coined this architecture quantum CCD because completely analogous to your CCD camera, you can move the charged particles around by changing the voltages applied to these trap segments here. So it's a divide and conquer approach. Yeah? So we can store a small ion crystal here which can be manipulated at high fidelity. and then I can bring in new ions in this processing zone, move other ions out, and this way I can scale up my system. And that's exactly the approach we try to realize in Mainz. So that's a sketch of a segmented trap, a bit simplified of course. So the yellow boxes here are the individual segments. So for each segments we can apply custom voltage waveforms. All the lasers for driving gates, etc. are directed to a single trap segment, that's the laser interaction zone. And then we can carry out different kinds of shuttling operations. So we can simply transport ions along the trap axis, we can split and merge these ion strings, and the particularly nice operation is that we can also rotate ion crystals. So why is that important? Such a rotation would constitute a decoherence-free swap gate. Yeah? So we get a swap gate without any laser addressing, without any decoherence for free. And as we don't need any lasers, these swap operations can be even carried out in parallel at different trap sites. Yeah? That's important because this way we don't have a 1D nearest neighbor connectivity, but we have some effective connectivity which goes beyond 1D. Yeah? So this can really render any quantum algorithm realization much more efficient as compared to a 1D system. The catch about these shuttling operations is that on the one hand, of course, we want to do them fast in favor of processing speed, but on the other hand, that's a really difficult thing here. We want to avoid motional excitation. Yeah? If you can imagine, if we move around these ions very fast, they start shaking in the trap, and if they shake too much, we can't do any high fidelity gates anymore. So that's the basic complexity we gotta deal with. Yeah? The trap we're working with looks like that. Yeah? So it's a microchip trap which is handmade by the students in our group. It's fabricated like that. So we start out with an alumina wafer which is laser cut with a given structure. Then we deposit metal on it by means of evaporation. Then in the second round of laser cutting, we create some electrode structure. So here you start these segments appearing. Then in another step, we even put more metal on it. In this case, it's gold because it provides a very clean, noise-free surface. And then finally, this trap is assembled. It's a multi-layer stack because it's still a three-dimensional structure. So building such a trap takes like a talented student half a year and costs like 50,000 euros. Yeah? So to give you a feeling for the dimensions, the width of this trap slit, so that's a volume where the ions actually sit, is like 1 centimeter or so. Yeah? So another crucial device we need for realizing this approach is an arbitrary waveform generator. So as I said, we need to supply every trap electrode with freely programmable voltage waveforms. So we need like 80 channels with a large memory depth. We also need fast update rates in order to do fast shuttling operations. And we have very stringent requirements on noise. So we've been developing such devices now for over 10 years or so, and we're currently in the process of commercializing them. Yeah, that's what an ion trap setup typically looks like in the lab. This thing here is a magnetic shielding box in order to shield off drifting magnetic fields. What you cannot see so well is an ultra-high vacuum vessel. Of course, if you work with single atoms, you have to suspend them in vacuum. There's no means of doing that under atmosphere. Yeah? Then all the laser light is delivered by fiber optics through such fiber cords here. Then there's some beam preparation optics inside the chamber. The radio frequency for driving the trap is generated by this resonator here. And that's where all the DC lines for the electrode voltages come in here. So it's quite a complex setup, and it requires very skilled PhD students to operate and improve this apparatus. That's a recent result which we see as a proof of principle for our shuttling-based approach. That's about scalable generation of multipartite entangled state. In this case, it's 4 qubits, so we start out with 4 qubits initialized in 0, and then we have a cascade of 3 CNOT gates for creating a 4-qubit entangled GZ state type. That's the most non-classical state you can think of, and in the end, we analyze the state by doing complete quantum state tomography. So what you see here is a shuttling schedule. We start out with 2 ions, entangle them, split off 1 ion to the left, then another ion comes in from the right. These 2 are entangled and so forth. And then in the end, we really subsequently read out all these ions. And we can fully reconstruct the quantum state. So you see here the density matrix for experts, which allows us to completely get the information about the state, and what we get is a state fidelity of about 95%. So that's quite remarkable for a 4-qubit GSZ state, and it proves that by means of this shuttling-based approach, we can really circumvent the difficulties associated with doing gates on larger registers and be limited only by the fidelity of the 2-ion entangling gates. Yeah? That's what we work on these days. I don't want to go into too much detail here. It's a sequence on 6 ions, which is QND syndrome readout. So that's an elementary building block for quantum error correction. The sequence is way more complicated as compared to the 4-qubit entanglement generation. And again, for this we need some kind of shuttling schedule, right? So this is shown here. There should have been an animation where this thing is moving here and showing the entire sequence. The bottom line here is it really becomes massively complex. Yeah. So as you see here, this is handmade. This schedule was conceived by a PhD student, but clearly that's not the way to go. So we need some software layers in the stack for automating these endeavors here. And in this spirit, that would be the trapped ion quantum computing stack. So as you see, our work indicated here by the gray arrows is more on the lower layers of the stack, which are rather hardware specific. So we don't work on quantum compilers, but then our work really starts on software architecture for automated generation of shuttling schedules, automated generation of suitable voltage waveforms, then as I presented you, development of scalable real-time control systems, and then on the ion trap hardware itself. Yeah? And in order to beat the complexity, because we really need some modern cutting-edge software engineering here, we've been teaming up with industrial partners. Also in order to get scalable, we need advanced ion traps, which we cannot build ourselves anymore. So that's a modern surface electrode trap fabricated by Sandia National Laboratories. So in this case, the ions are not trapped inside the volume of the trap anymore, but this is a 2D electrode structures, and the ions are trapped above the surface here. And this allows for using fabrication methods which are borrowed from microchip industry. And the big advantage here is that the complexity of the structures you can fabricate is absolutely increased. So this trap has like, I think, 180 electrodes. So in the end, it could allow for a confinement and manipulation of like 60 to 80 trapped ion quantum bits. Yeah? So this is fabricated on the basis of semiconductor technology. That's what it looks like in real life, but yeah, currently the fabrication and also the noise generated by these surfaces here is not entirely understood, so currently people are trying to learn how to use these traps in a reasonable way. Yeah? So we come back to our comparison of platforms, superconducting circuits and trapped ions. So I hope that I could sort of convince you that superconducting circuits are not the only viable trap platform for realizing quantum computers. The race is by no means closed. Both platforms certainly have their issues. Also, both face the difficulty that they are bulky. Yeah, so trapped ions repel each other. It's charged particles, so there's no indefinite way of miniaturizing them. And also superconducting circuits require microwave resonators, which have extensions in the micrometer or even millimeter range. So concerning scalability, that's really the big open question on how to create devices of 1,000, 10,000 or 100,000 qubits which operate in a reasonable way. Yeah? Also concerning company support, this has increased for trapped ions a lot. There's also startups working on trapped ions and also big companies. And also concerning the pros and cons which are listed in the table here. So one thing which is often conveyed as a big disadvantage for trapped ions is slow operation. So first, in my opinion, operational speed is not the key issue for quantum computers. The key issue is intrinsic parallelism. Yeah? So the processing rate for quantum computers simply doesn't matter so much. And also most of all trapped ions are actually not so slow. I've been showing you that entangling gates are possible on a timescale of 1 microsecond. So trapped ions are really catching up here as compared to superconducting qubits. And then again, trapped ions are made by nature. Every trapped ion in my trap is identical. It's always the same kind of atom with the same level scheme. Yeah? So I can rely on that. For superconducting circuits, that's not the case. There's always fabrication variance, and that's what people have a hard time of getting this under control. Yeah? So the qubit frequency is varying by 10% from qubit to qubit within a given superconducting qubit device. Yeah? So on the other hand, the fact that superconducting circuits are man-made is also interesting. Yeah? It allows for tailoring the devices, of bringing in new ideas from material science. So in this spirit, of course, superconducting qubits are doing fine. Yeah? I don't want to advocate against them, but the race is really still open, and it's unclear which platform, if any of the two, will finally prevail. So that's the take-home message. The race between trapped ions and superconducting platforms is still open. Also, scalability is completely unclear for both platforms. And for both platforms as well, it's very likely that we see some more NISQ applications, some demonstration of quantum supremacy, and the demonstration of building blocks for quantum error correction in the near future. So that's our group, that's people working on this project, and we get funding from the European Union within the current quantum technology flagship, and we also receive considerable funding by the US federal agency IARPA. Thanks a lot.
Do we have any questions?
Also somebody else maybe? Two questions actually. The first would be, I think it's a good way, it's a good approach to try to use the semicon processing to make this, because it's established and this is, I think, likely scalable. But what do you think is the main challenge? Is it more like processing, getting the structures right, or is it something like materials related, getting the purity of the materials right?
So you say it's a good idea. I know some people actually working with such traps. They will perhaps have a different opinion. So these semiconductor surfaces or the bulk generates electric noise, which is not entirely understood. So you simply have a hard time with taming your ions properly, cooling them to the ground state, keeping them in the ground state, also getting stable larger ion crystals, and I would say it's currently really unclear, so it requires a lot of material science.
Okay, so open race, if I understood you correctly.
Yeah.
Okay. So the second question is maybe coming back to Michael's talk from earlier. I think he made like a projection where he expects like the qubit count to go over time. Yeah. Do you agree to this, about this like plateauing? Do you have a different view?
My view is exactly the same. So I think with classical macroscopic Paul traps and also with segmented Paul traps, we will see qubit reach the sizes of 100 in the near future, which will also allow for demonstration of quantum supremacy just by doing random unitaries. It's of course a bit meaningless, but it's quantum supremacy. Yeah. But then going from 100 to 1000, I don't see this within the next couple of years.
Do you also see quantum advantages possible? Or do you think that there will be a barrier?
So I think with 100 qubits you can demonstrate quantum supremacy, but in a useless way.
Okay.
Yeah.
Two questions also. First, What are the requirements to do that open PhD and postdoc positions?
Degree in physics, perhaps, or some related field.
Okay.
Computer science would also be nice.
Okay. And second is regarding, so to do the trap ions, right? So you pass a laser to one electron who is in the external orbital, and you take that electron, and then I saw in one of the slides that that electron carries one atom also.
Yeah, so the alkaline earth atom has two valence electrons, and one is shot away with a laser, and then you're left with an ion. But there's of course not only one laser, so for operating these qubits there's quite a few lasers, so like about 12 laser beams or so.
Because when you take that electron from where is the other entanglement electron?
So at this point we don't have any entanglement, that's just for preparing the atoms. So there's a laser for this photoionization, yeah? Then there's lasers for cooling, there's a laser for readout, and different lasers for doing the gate operations. Yeah, so I didn't go into the full complexity here.
Just with the danger that I maybe misunderstood the physics completely, but isn't it maybe possible to use a Bose-Einstein condensate as a medium for the calculation?
Well, there's also proposals for quantum computing with neutral atoms, also in condensed phases, yeah, but that's on the level of proposals. Yeah, so that would be matter wave interferometry on atom chips. There's people doing this kind of stuff, but as far as I know, there's really no properly demonstrated qubits so far on this basis, or even multi-qubit operations.
So you're talking about the race between different hardware technologies.
Yes.
So what is your criteria for the winner of the race?
It's all about scalability.
Okay.
So increasing fidelities, it's a matter of technology. Increasing speed is a matter of technology. But really, the platform with the key idea towards scalability is winning.
So if we look at classical computing, we can say that there were different inventions that had an effect on the way classical computers were built and becoming scalable systems in the way of commercializing. So what do you think about quantum computing there? Because if we look at sensoring, we could also talk about nitrogen applications.
So I think, I'm not clear what the question is exactly, but so vacancy centers are still like around as a candidate, but I don't know if any big company or any large public funding program seriously working in the direction of realizing a quantum computer based on vacancy centers or related platforms, because these are just too hard to control. Yeah. So that's more interesting for quantum sensing.
Yeah, I mean, regarding how this area is maybe influencing quantum computing. So if we are making big efforts on quantum sensing, this might lead to other advances in quantum computing.
Yeah. Good question. So one could think of like integrating quantum sensors in such a quantum computing device, because I didn't talk about this, but one big challenge for a quantum computer is that you have to do a lot of calibration all the time. Yeah. So if you want to have if you don't want to drown in calibration effort, you need efficient and reliable methods for calibration. Yeah. So in this sense, quantum sensors might actually help.
Yeah, I mean, I have heard this idea about these microstructure traps. I mean, it's around since 2002, and you pointed out already that it's difficult. So what is stopping you from using it?
Exactly.
now?
So first, the people doing this are all from the field of atomic physics. So we know how to use lasers and so on, and ultra-high vacuum chambers. But we first really had to learn how to build these traps. That's more like condensed matter, experimental condensed matter physics. Yeah. So it was a long way to go to learn how to produce these traps, how to get them reliable. And building such a trap, as I said, takes half a year and a lot of money. So you have a hard time doing statistics on that. So you build a trap and then you hope that it works. Yeah, and if it doesn't quite work, you will hardly ever build a second one as a PhD student. That's actually the bottleneck. Yeah.
Okay. Any other? Oh yeah.
I'm afraid I haven't exactly understood the technical details of measuring the quantum states when they are in these Hall traps. In which explicit way do you do that? Is it you explained that with these emissions that you mentioned?
Yeah.
How is that explicitly done in your example?
So you shine a laser beam onto a specific ion. If it's bright, it's in state, say, 1. If it's dark, it's in 0, right? So that's the binary information you get. And then if you really want to reconstruct a quantum state, you have to do tomography. But that's the same as in any other platform.
Okay, and is that easily realizable if you have so many quantum bits in such a
At least for 4 qubits, we were able to show it, yeah.
I think this question was about scalability. How are you going to increase that? If you have 2 chimes for every laser, it's going to take a lot.
Yeah, well, that's a basic question about scalability. It's not only about readout, but it's also about the gate. So you have to store a lot of qubits in your whatever device, and then but still you have to be able to talk to each qubit individually. So that's the same problem for every operation on the qubit, and the same problem for every possible platform, and it's unsolved.
Maybe a short question. Did you see this recent announcement by IMQ with like 160 qubits on? Was that a linear Pauli trap? Was it just a simple linear Pauli trap?
That's a simple, old-fashioned linear Pauli trap,
okay.
which is cooled with liquid helium.
I see.
Okay, any other question? No? Well, thanks to the speaker again. So now we're coming to our last talk. We'll just take right here. Nothing happens.
Mein Schalter ist ziemlich kompliziert.
Yes. Okay.
Okay, not the put. Yeah, no.
Okay, the last talk is from Michael from the data lab from Volkswagen, and he will talk a bit about the applications on the automotive side. So,
Oh no. No, that's right.
Gehen wir in die Richtung?
Hm?
Passiert wieder nichts. Okay, das ist die Frage. Just grab another sandwich. We'll continue shortly. Okay, so now the talk from Volkswagen. Thank you.
So, yeah, thank you. And thank you also for hosting this event. I think it's pretty cool to have also some quantum computing events here in Germany, and not only in the US. And especially, can you think about everything better than having a quantum computing event on Friday night? I can't. So I will speak about quantum computing for applications in automotive industry. So my talk will be a bit different than the other talks. It will be more an overview what we do at Volkswagen, not that technical. So let me start with presenting the team to you. So we actually have 2 locations. We have one team at the data lab in Munich, and the second team at the code lab in San Francisco. And we both work together. And as we learned from the previous talks and also from the talks at the first meetup, quantum computing is not only about understanding the quantum effects and the quantum information theory. It's also about understanding the problems you would like to solve. And that diversity is also in our team. So we have very many different skill sets in our team. So for example, we have machine learning researchers who help us to understand the bottlenecks in classical machine learning, so they know what we can do classically and help us to understand what we have to improve quantumly. We also have data scientists which help us to extract data which we need to, for example, formulate optimization problems in such a way that we also can use a quantum device for that. We also have physicists, because you also have to understand the quantum information theory, you have to understand quantum effects, and it's always good to have physicists in the team. By the way, I'm also a physicist. We also have computer scientists, and that's also very, very important, because in the end, what you want to do, you want to solve some problem. And complexity is a very difficult thing. So if you solve a problem, but a problem you solve is easy, then quantum is maybe not the right thing. What you want to do is you want to solve problems which are hard. And distinguish between problems which are hard and which are easy is a very complex thing. And therefore, computer scientists are necessary. So, why are we interested, or why is Volkswagen interested in quantum computing? And that's a question I'm being asked very often, to be honest. So also when I visit my parents back home, my mother is asking me, Michael, what again is that what you're doing? And I tell her it's something with quantum physics. And then she asked, okay, why is Volkswagen doing that? And that's a simple question, but it's a valid question. But there's a simple answer. Many future problems will be not efficiently addressed anymore by classic computer systems. And all of these problems we also have at Volkswagen. So think about transportation and logistics. We have many transportation and logistics problems already now at Volkswagen. But when we will have like thousands and millions of connected and self-driving cars on the street, we will produce so massive data that we are not able anymore to optimize and process this data. So, for example, think about you're sitting in your car in like 20 years in your self-driving car, and you want to go from A to B. And then you have to wait like for 1 hour until your car gives you the route because it's just too much data. That's not something you would like to have. You would have it immediately. And that's something where we hope that quantum computing can help, that we can process and optimize this data more efficiently. Machine learning is also a thing which we look into. As we heard from the other talk, machine learning is a hot topic itself. And when you combine it with quantum computing, it's getting hotter. So machine learning, we also have at Volkswagen. For example, think about self-driving cars. You have a lot of sensors, and you want to predict something with machine learning models. And if you have too much data or too complex correlations in your data, it gets very tricky to train your classical machine learning models. And so we also hope that at some point, quantum could be helpful. A very hot topic, which is closer to now than the other ones, is simulating physics and material science. This is what Michael is also doing, namely simulating quantum system itself. Because in the end, a quantum computer is also a quantum system, so it's very good in simulating quantum physics. And there we have plenty of use cases at Volkswagen. For example, it could be the skeleton of the car. We want to find a better skeleton of the car, then you have to simulate it. We want to find better batteries, more advanced batteries, then you have to simulate it. So you have to know what exactly is going on in the system you want to make better, and therefore you have to simulate it. And as Michael told us, simulating already smaller quantum chemistry systems exactly is not possible with classical systems. So this is an area where we hope that quantum computing can really help. So what we did as a first project roughly 2 years ago was a kickoff project, so to say. We wanted to do something which everyone understands and also which is somehow emotional. And what we did is traffic flow optimization. Everybody understands traffic and everyone knows traffic jams. And most people I know do not like traffic jams. So this is a topic, when you explain it to someone, everybody gets it. And that's what we did in the beginning. We tried to solve a traffic flow optimization with quantum hardware. So what we did, we took data from the city of Beijing. So here on the left-hand side you see the traffic in the city of Beijing for 10,000 taxis. And this is now something which we would like to optimize, because you see we have a lot of red spots in this picture, so where the traffic flows not smoothly. So what we would like to have is just green areas where the traffic is going smoothly. This problem on the left-hand side was actually, it was too big for the chip, so we were not able to do that. So we had to break down into a smaller system just to such that it fit on our quantum device. And what we did is we took a subset of the problem, namely just the cars going from the city center to the airport of Beijing. So this is just 480 cars, and these 480 cars we want now to rearrange such that on average all cars come to its goal fastest, so to the airport. So what we did is now we said, okay, each car now get 3 different possible routes. And now what's the best assignment of the cars to that routes? And this is the question we solved with quantum computing. And what we did, we used D-Wave, the quantum annealer built by D-Wave, which we already heard several times tonight. This is a special purpose quantum computer, so it's not a gate model device, it's also not iron trapped. It's a special purpose quantum computing to solve optimization problems. And for being able to solve optimization problems with a quantum annealer, you have to translate your optimization problem to a language the quantum annealer understands. And for the quantum annealer, that language are classical spin class systems. So classical spin class systems are just systems which describe, so to say, the interaction between your qubits in the system. So you just have like many qubits in your quantum computer, and the spin class system describe how these qubits interact in the system. So what you have to do is now, you have to map your optimization problem to these interactions of the qubits in your quantum computer. And then if you solve this spin class system, so if you find the minimal the minimal energy of the spin class system, you also find the solution to your optimization problem. So that's what we did. We mapped this traffic flow optimization problem to the spin class system, and we found the best configuration of the traffic flow with the D-Wave quantum annealer. These are the results. So here on the left-hand side, you again see the unoptimized plot where we have traffic jams, and on the right-hand side, you see the solution which we got back from the D-Wave machine. So what you see here, we don't have so much red spots anymore, and we have more routes. So the cars are spread on different routes such that all the cars come to the airport fastest. And that was our first project, and first, so to say, at least proof of concept that we can use quantum computers at least to do something. I'm not saying that we use them to do something useful, but we use them to do something. And that was already something which was new to the field, and also something which sparked the quantum computing community a lot, especially in industry. It was before that it was more like something which physicists do in their cellar. So this was our first project, and it was a huge success. We presented it at CeBIT 2 years ago, and we got like big media coverage and a lot of questions, and so it was a great success. But as I said before, this was just a first like toy problem, just to show that we can use quantum computing. And now after that we wanted to start to dig into deeper in these subjects and see if we can also do something more useful which really brings value to Volkswagen with quantum computing. And what we do there is now we have different projects and investigations. So what we look into is quantum machine learning, and there we want to enhance existing algorithms, for example reinforcement learning or clustering, also binary classification, and we want to see if we can enhance these algorithms with quantum computing. And a very important point here is that therefore we have to understand the bottlenecks in the classical algorithms. And therefore we have also machine learning researchers in our team. They help us to understand where the bottlenecks are. And we are also looking into optimization algorithms, and there we also want to find a more powerful way to solve optimization problems with quantum computing. And a very important point here is also, like you saw just now, the traffic flow optimization thing. Here we want to find problems which are suitable for quantum computing. We don't want to just put anything on a quantum computer, but we want to find the suitable problems and also the suitable algorithms for that. And therefore we have to know the optimization problems very well. And we have to know also the complexities behind the optimization problems to tell if a problem is hard or not. The last thing which we are also interested in is material simulations. In the end, this all goes in the direction of Michael's talk. And for Volkswagen, one hot topic is also to find advanced batteries, as you can all imagine. So, as we heard a talk about machine learning today, we heard a talk about quantum chemistry today, so I will talk a bit about optimization problems. You already saw the traffic flow optimization, and actually we have two different possibilities with quantum computing to solve optimization problems. Namely quantum annealing, which we used for the traffic flow optimization problem, but we also have gate model devices, as for example the ion traps. So we personally, we work with, closely with Google. They have a chip with 72 qubits, superconducting qubits, and plan is that we use that chip to also study optimization problems. So I will talk a bit about gate model devices and how to use them for solving optimization problems. So we already heard this today, hybrid algorithms. These first gate model devices are very small, so you have only a few number of qubits. On top, they are very noisy. The fidelities are bad, we have readout errors, we have decoherence effects, and this all destroy, in some sense, your quantum computations. So the problem is that with these first NISQ devices, you are not able to run like Shor's algorithms or Grover's algorithms. So what you can but instead do, you can use hybrid algorithms. This is something which seems promising for these NISQ devices. And hybrid algorithms, as already explained, are parameterized quantum circuits that are optimized in a classical learning loop. So the idea is to combine the power of both worlds. You want to combine the quantum power with the classical power. That picture actually shows the same picture as we saw before, but I have to admit the picture before was a bit more pretty than mine here, but it tells the same. So we have a quantum part. The quantum part now spits out, so to say, let's say a guess to your solution. So you ask your quantum computer, give me please a solution to my problem. He gives you back a solution. Then you put it in a classical computer. The classical computer checks, is it a good solution? And then the classical computer says, for example, no, it's not a good solution. Tell the quantum computer to use different parameters. And you do this in a clever way, iteratively, and hopefully in the end, you find the solution to your problem. So the idea behind this concept is that you use the quantum computer to do the hard part of your problem, namely simulating the physics, and the classical computer just to optimize the parameters you put in your quantum computer. And this kind of hybrid algorithms you can use for different things. For example, for quantum chemistry, we have VQE, which Merkel is using. We have QNNs, quantum neural networks, which is a hybrid algorithms for quantum machine learning. And we have QAOE, the quantum approximate optimization algorithm, which is used to solve optimization problems. And this is what I would like to talk. So there's my talk. So the quantum approximate optimization algorithm is, as I said, used for solving optimization problems. So it's similar in some sense to quantum annealing, because the goal is the same. You want to use a quantum device to solve a classical optimization problem. The difference is that instead of doing a quantum annealing quench, you're using a sequence of gates which encode your problem. So in this picture, HP is encoding the optimization problem you want to solve, again in a spin class Hamiltonian, for example. And HX is just an operation which, so to say, brings into, let's say, randomness into a quantum computation. And this kind of setup is in general able to solve optimization problems. And in general, it's also able to mimic quantum annealing. But what we actually showed is that quantum QAOA is able to solve optimization problems where quantum annealing fails. So QAOA is in some sense more powerful than quantum annealing is. For QAOA, as I said before, you do the same as for all the other hybrid algorithms. You optimize your parameters classically such that the energy of your problem, which is encoded in HP, is minimized. And at the moment we are doing a lot of research about QAOA and want to find out what kind of optimization problems can you solve efficiently with QAOA, how does it has to look, how shouldn't it look like, and this all would enable us in the near future already to solve industry problems with QAOA. Not industry problems we cannot solve with classical computers. I'm not speaking about that we will put like in one big quantum computer to Wolfsburg and solve all the optimization problems, but we are already now interested to know the optimization problems at Volkswagen on a smaller scale for being ready maybe in 5 or 10 years to solve the big problems. And that's the idea, that we also know where can QAOA help us with this task. I think it's already my last slide, so I think I was a bit fast. So what comes next? What we would like to do next is also to do a lot of research to find more suitable applications and algorithms. And therefore we work very closely with our internal business units. The business units do have the problems. They know what kind of problems are hard to solve and where the classical bottlenecks are. And this is very important for us, because otherwise we just are doing research and we are not knowing for what. So these internal business units are very important for our whole research, because we know what the goal is and we know what the benchmark is. And that's also something which I personally see as a problem in the whole quantum computing community, that some people do not concentrate on the problem itself, but just on doing something. And I think it's very important to always have the goal in mind. On top, we also work closely with our research partners as Google or D-Wave or several universities around the world, and they help us to find suitable algorithms, to understand the algorithms, and also have a look with us on the optimization problems. So in the end, we try to form a network out of people understanding quantum algorithms and people understanding the problems, because these things have to be together. Otherwise, you are not solving a problem, or you can't solve your problem. Yeah, thank you.
Felix?
So, what are you asking your business units in order to get the right problems from them?
So that's a good question, because it's not just that we drive to Wolfsburg and asking them, so do you have anything for quantum computing? Because most of the people do not know quantum computing. And therefore what we try to do is we try to really get deep into their subject and try to understand their problems, so that we are able to extract problems. And what we also do is we also explain them what we think is a good problem, so that we can find something together. But yeah, that's not an easy task, because if we don't know the problem and they don't know quantum computing, it's not always easy to come together.
I mean, how you said you compared quantum annealing to QAOA,
yeah.
And you did that by the advantage comes from different driver terms, or
no? We used the classical driver terms for as in QAOA, and what we did is we analyzed different problems by their spectral conditions, and for some spectral conditions, QA, so quantum annealing, always fails.
What spectral, like cloak?
Yeah, yeah. But QAOA can succeed.
Because it finds it kind of ramps up and then makes slow and basically.
That's also my picture. QAOA is able to use diabatic bumps. Quantum annealing is not, and so sometimes the adiabatic evolution is not always the best.
Okay.
So you already presented at CES in 2017, right? At the consumer.
No.
Okay, then this one. With an actual problem you solved, right? So I wonder
your perspective, why is automotive amongst the early adopters when it comes to quantum computing?
I mean, we have many different computational problems in automotive. We are interested in battery research, we are interested in optimization problems, we have machine learning. So we have all of these computational problems we have at Volkswagen. And that's so it's not that, for example, I think it's different in pharma where you only focus on quantum chemistry, for example. At least I think that's the case. And so we all have all of the problems at Volkswagen. And that makes it, at least from my perspective, easier to pick the right ones.
Well, yeah, that's an interesting point of view. I mean, you also have like supply chain and
Exactly.
other things you could look into in other industry as well, right? Not only automotive. So
that's true.
okay, but still, you think it's just the number of potential use cases that made it that attractive for automotive?
Also that, but we were also one of the first ones. We were actually the first one, I would say. And I think in the next years, many different companies will also jump on the quantum computing train. So I think it was just a coincidence that we were the first ones as well. And now, as they see that it makes sense already now to invest in quantum computing, I mean, in the last year, many companies jumped on that train.
Okay. Thank you.
Okay. The problem discovery issue sounds like something a machine learning team might encounter still working completely classically. Have you worked together with your resident machine learning teams to exchange techniques for finding the right problem for your solutions?
So for what problem? For the traffic flow optimization problem now, or for
like,
in general?
You described how it's difficult to find the right problem for quantum computing. It sounds like something a machine learning team might also encounter, find the correct problem for machine learning. So have you experienced some cross-pollination, like exchanging techniques for finding these problems?
So we are in strong contact also with machine learning teams for finding, for understanding the bottlenecks of classical machine learning, but also for finding the right problems for quantum computing. But in the end, so I think finding a suitable problem might be hard for classical machine learning as well, but the tasks are different, I would say.
Okay, so you wouldn't say there is some idea how to approach a other colleague who might have a problem and get to find out together with you what the problem might be. So you haven't found some nice general approach.
So a general approach how to find suitable problems for.
So you have
no, unfortunately.
So, two questions. The first is, what led to the decision to change from the D-Wave annealer to the Google's Bristle cone? And the second is, so what we see at clients is that when you deep dive into optimization problems, often you find solutions where you can really twist like the classical solutions a little bit to get better results. Do you see the same effect at Volkswagen?
So first we are still using also D-Wave. So we are using both. We are having a look at quantum annealing and gate model devices. For this project which I presented here, QAOA, this one's on a gate model device, but we also have projects with quantum annealing. And yeah, that's true. If you use post-processing on D-Wave devices, like single spin updates, if you're lucky you find a solution, that's right. You could imagine that similar things also happen to QAOA, but this also depends strongly on the problem. If you have a very complicated problem where single spin updates are not helpful anymore, and you need like multi-spin updates, this gets expensive classically very fast.
Question from my end. How do you see the role of the startup community, specifically for automotive in quantum computing?
So, in general, I think startups are a fantastic thing to also develop new ideas, to find new algorithms as Michael's startup. I think that makes very much sense, and we at Volkswagen are also collaborating with startups, because startups also help us to understand quantum computing even better. And I think startups make sense in all kind of fields, not only automotive.
So do you also work with, does this mean that you work with hardware and software startups, or how do you select?
How do we select?
Yes. Just looking at the map Matthias showed earlier, so there are many startups around. So what are your criteria?
So with the hardware provider, so to say, we are settled for the moment at least, but we still also like open for new partnerships. Not like that we say, okay, we don't talk to anyone. So I think also, for example, Rigetti is also still a startup. It's a pretty huge startup, but still I would call it startup. But they call themselves startups. So also this is very interesting for us. So, yeah.
Do you see any fundamental differences if you look at automotive versus other industries? I mean, I know industry-specific startups like HQS, for example, or like Yoast Quantum, which are dedicated to chemistry or finance. But I don't know any which are saying, okay, I'm like the go-to startup for automotive. Is there like fundamental reasons for that? Or
for automotive, for quantum automotive, so to say.
So there's like no Yoast Quantum, but for auto, even though automotive is like the dominating industry in Germany.
I think the difference is that, as I said before, that automotive itself is not a problem. It's a company field, so to say. And quantum chemistry, this is like a research field, and also financial things are a research field. But I mean, a quantum automotive startup would have to tackle different things, like batteries, like machine learning, like optimization problems. So I think that's the reason that startups go more in the direction to pick some things where they advance and not like try to build everything at once. I think that's the main reason, but that's only a personal view.
Interesting. So it's actually not the fact that it's really the fact that it's so broad.
Yeah, I think we have a broad bunch of on topics. So it's not only about quantum chemistry. It's about many different things. So I think that's also the reason. I think startups, I mean, they have to specialize more on a specific thing. I think Michael cannot say now we are starting a quantum chemistry startup and also do machine learning on the side. I think that would be good.
Maybe a question there are startups who claim that they are essentially doing everything. I think Zapata is maybe one example. They essentially say, okay, we're doing like chemistry, but also finance, but also quantum machine learning. So wouldn't these guys be perfect for you then?
Yeah,
they can do everything apparently.
Yes, but I would also say so Zapata's origin is a robotics group, so they have a knowledge in quantum chemistry, and yeah, they're doing more things. But I think that's also natural. If the startup grows and if you get more money, you have to spend it. And I think
well, you can save it.
Yeah. I think spending is better, and then you can also have a look on different things. But yeah, I never worked for a startup, so maybe Marcus is the right person to answer these kind of questions.
I mean, that was a good answer. It's always like you focus in the first place. You focus on your main topic, and then you start to grow and start to get more attention. Of course, you can hire more people who are also specialized in other fields and start to grow your knowledge.
Yeah.
But in the first place, you should start at one part.
So what's the next topic for you?
Automotive probably. There seems to be a market.
I mean, if there's a need, there are also less competitors, right?
Sorry.
Yeah, thank you. I have a very, let's say, controversial question.
Yeah.
You know, I simply don't see what you're doing makes sense, right? Because you say traffic problem, and actually traffic is the problem.
Yeah.
There is no need for more vehicles there. You know, I mean, being electric or non-electric, this is not the problem. So, and also, you know, thinking about, you know, looking at traffic and trying to predict it and so on. I mean, there should be less traffic. There should be less cars. That's the issue. So, I mean, it's not. There is not maybe even a question what I'm saying, but I just find it a bit waste of effort.
So for us,
sorry for being so critical.
Yeah, that's like, I would say, more a philosophical question. So for us as quantum computing people, we wanted to solve optimization problem. And if we say, okay, we don't have any cars anymore,
years you will
then
not
that
have a problem, because I mean you said your timeline is 5-10 years.
Yeah.
So you know that basically there are climate problems, right?
Mm-hmm.
So in 5-10 years you may not have problems to resolve. It's just I'm just trying to find like a reason behind your research, and I cannot see it.
So I would say for the traffic flow optimization, it was just to solve an optimization problem. It was that we wanted to see if we are able to use a quantum device to solve optimization problem. It was not particularly about traffic, but it was just about solving the optimization problem.
I think we can also discuss this later with the beer. I think philosophical
No,
questions are always better.
I'm too tired. But the thing is that you need, like, if you're trying to do something, I think you need to ask yourself some fundamental questions first. And it just looks like, I don't know.
The fundamental questions, I would say, here is on the quantum computing side.
Yeah.
Sorry, can you speak a bit louder?
Sure. I was wondering if using complex networks wouldn't make more sense to predict traffic. Is one point. And second, well, I have worked in lithium-ion battery interfaces for another automotive company for a while at university, and there was a lot of sophisticated quantum calculations on one side, and that is the hybrid model, classic part. But in the end, we were just matching parameters with some force fields, and you didn't get rid of that uncomfortable feeling. So I guess whatever we use now, will get more beautiful, but still we just match parameters in the end. Is it kind of okay, or is it just me not having a good feeling?
So I'm not sure if I got a second question, but so the first question about traffic flow. So you are right. This traffic flow optimization, we never made statements about that we solved this in any way faster than with a classic computer. There may be many classical algorithms which solve this problem faster than we did with the D-Wave quantum annealer. It was just to show that we can use the quantum computer already now to solve something which is in the real world and not just a physics example.
Maybe, did you ask if you did do quantum chemistry calculation and match them to force field calculation for batteries? Yeah, I think if quantum computer is going to be used, it's going to be used the same way. Yes, yeah, I don't know. I mean, but I think in the end you have too many configurations to test on the quantum computer alone, so you have to match the force fields in the end and make your force fields better.
That made me leave university.
I'm sorry to say, but I think it's going to stay the same, unfortunately.
Okay.
Okay, we actually have a question from one of the YouTube watchers. Just read it out loud.
So, are you planning to implement a specific application in your self-driving cars in the near future? I think we definitely plan to implement applications, but at the moment not quantum applications. So quantum is still in the phase where we try to find out what are the suitable applications. It's not about putting a quantum computer in the back of our car. So this will maybe most likely never happen. But it's about finding the suitable applications in the company and how we can solve them. And we are not thinking yet about these kind of questions, how to, in the end, put applications in the car.
Okay, there was a follow-up question.
Yeah. And what type of device would you use, D-Wave or Google system? Thank you. So we use both. We use D-Wave and Google. It depends on the application, I would say. For something Michael is doing, except D-Wave is doing a lot of progress in introducing new couplers. For quantum chemistry, gate model devices are more suitable. But for optimization problems, we also are looking into D-Wave, and we want to also compare these two things. If we can, for example, use the D-Wave machine for some optimization problems better than we can use gate model devices. Yeah.
Quick one on the machine learning part.
Yeah.
You mentioned you're also looking to machine learning. What particular things are you looking at? I think you mentioned clustering. Are you looking into generative models as well, or is it more traditional?
So we do different things. We are also looking into generative models, and we are also looking into if there are any possibilities to avoid the burn plateau of the Google guys. This is something we are doing, and we will, by the way, if you're in Rostock, are you going to the DBG? Rostock? No. We have some machine learning techs also in Rostock. Don't think so. The German Physical Society is...
APS March is much better.
The
APS March meeting is much better.
But they also don't film, so this is more advanced than the APS.
It's live.
Okay, if you have any other questions, you can just ask afterwards at the beer, so thank you again. And thank you all for coming. Please have a beer, please have a sandwich over there and start networking. And thank you all for watching online. I think it's 7 guys now. Thanks and bye.
Nice to meet you. So I was design for philosophical reasons. I was interested why we became